lesson, right?
No.
Okay. Okay, let's talk about properties of waves. Did I start this? I did too. Okay, so today's topic is, we're really just kind of building into the concept of waves. Big unit is talking about basically circulatory and oscillatory motion. Okay? If I were to ask you how they're similar and or different, hopefully you'll be able to answer and say, well, they're similar in that they both have like a period and a frequency. Something is either going back and forth in a nice steady motion over and over again, or it's going around in a circle in a nice steady motion. But at the end of the day, it has a very repetitive sort of pattern. Today we're going to talk about one very specific type of oscillatory motion, anything that forms what's called a wave. And so I'm going to give you some examples today of what waves are. We'll talk about some more, we're going to use some properties today, we're going to talk about types of waves in the future, and this is a very theory-based section. There really isn't any math to them. We're not doing a lot of calculations. So I'll start off just by reading my notes here. Most of the time when you think of a wave, you think of water. Right? I threw a picture of a guy surfing on there, and that is a wave. And honestly, that's not incorrect. Like, that is a wave, right? It's just maybe it's a very narrow idea of what a wave can be. Right? Does that wave, as it goes through the ocean or whatever it is there, is it probably the only one that will exist? Well, I mean, normally when you're on the water, right, normally a wave comes by, and then however long later, then there's another one, and there's another one. Right? And so it does have sometimes a very periodic motion to it. So I have down here some more bolded words. We're going to talk about what are called mechanical waves. And I mean, the wave that you have in the water is a type of mechanical wave. It needs to move through some sort of medium. Right? And here's some examples of mediums. Air, for example. Anybody think of some examples of waves that travel through air? Sound waves, yeah. And any sort of like wave, like for example, electromagnetic radiation. We have a whole unit on that in grade 12, but it travels according to a wave. So your cell phone is constantly picking up a signal. Does that make sense? Well, the signal would be in the form of some sort of wave when we talk about that more. So air would work, water would work, obviously. I did a little quick demo one day where I took a spring and I put it on the floor and I kind of waved it back and forth. That's an example of a wave where you can actually physically see it happening. So, what I want to talk about today is more of a math lesson actually than a physics lesson. This is something that you guys study in Math 30-1, and there are some extreme parallels between what you guys need to know in terms of curriculum for physics as what you need to know for curriculum for math. So for those of you guys at Livingston who've already talked about this, that's awesome. For you guys here, you're all kind of getting like a bonus lesson for what you learn about in the future anyways. So this is basically what a graph of a wave would look like in math. So basically it goes up and down and up and down. And this is known as a sine graph. If you were to take your calculator and graph y equals sine of x, this is what it would look like. You guys have your graphing calculators nearby? I think we've actually talked about this a little bit already. So type in y equals sine of x. If you were to graph that on a 10 by 10 graph, though, there's a chance it's not going to look like what my graph on there looks like. Did I explain why? Do you guys remember? Yeah, we actually want to put it into the other unit of math for radians. Or, here's the other thing. When you have a wave that goes, say, up and down or around a circle, it's all based on, well, it's based on a circle. How many degrees are in a circle? 360. So currently my graph is set to go from -10 to 10. Well, that's just not enough. If you were to make it go from, say, negative 360 degrees to positive 360 degrees, then hopefully on your graphing calculator you'll be able to get a graph that goes up and down in a wave pattern. Is it able to get that to happen? Eventually, everyone will be in the same place in math. Eventually, we won't necessarily work in degrees. We'll use the other unit of measurement, which is known as a radian. Remember how the formula for velocity is like 2 pi r over t? There is an equivalency between units of angles that's based on 2 pi. 2 pi is like 2 pi is actually the definition of a radian, actually. I don't want to do too much. You guys can actually see how right here, On this particular graph, 2 pi is kind of written there. If we wanted to change our mode into radians and change our window to go from, like, say 0 up until 2 pi, you could actually literally type in 2 pi if you wanted to. You might also get a nice picture of what a graph would look like, where the graph goes up and down. So today I want to talk with you basically about how this would look like as a graph from a math perspective. Okay, grade 11, so I'm going to put you on the spot. We've been talking about lots of different graphs in our course. And the ones that in math I need to require you to know are absolute value, reciprocal, linear, and quadratic. But this is a graph that we could work with. All graphs have a leading coefficient. What is the leading coefficient of this graph? Where would a leading coefficient go in terms of an equation? Well, it goes like before everything, right? What number is written before anything? Yeah, 1. Right? And so this graph has a leading coefficient right now of 1. Right? If we were to change that, I want to talk about how that affects your graph. What if I were to put a leading coefficient in front of this of 2? How would that affect the graph? It's almost kind of hard to see without putting them side by side. Let's do another one. Do one with 2, and do one with, say, 8 sine x, just to compare. How would this affect it if we change the leading coefficient of the graph? What happens to it? It gets taller. Yeah. And so today we want to talk about some of the terminology that goes along with this graph. What's actually been affected here is called the amplitude of the graph has gotten taller. It's gone from an amplitude of 1, when the leading coefficient was 1 and we didn't even write anything. That was the amplitude of the graph. That's how tall it was. The second graph had a leading coefficient of 2, which means that it has now an amplitude of 2. And the last graph I threw on there now has a leading coefficient of 8. In a real-world scenario, imagine this represents a pendulum. Well, if you increase the amplitude, all it means with the pendulum is you just pulled it back further and it's swinging further. Does that make sense? Or if this is a circle and it's going around in a circle in some sort of way, well, this one right here is a very small circle. It goes up a little bit and down a little bit. It goes up a little bit and down a little bit. That's a little circle. Whereas this one here goes up a lot and down a lot. That's a bad circle. Hopefully you get the point here. Why don't we talk about some of the measurements you want to have on these graphs then. So the first thing is, in math, we often base these things on either degrees or radians. Okay. So those are the 2 angles we often work with. In physics, though, we're going to change things. This axis right here for the y-axis, and this axis for the x-axis right here, usually they have to represent more than just y and x. Like we can't just say x and y. It has to have some sort of unit associated with it. So along this axis right here, the x-axis, it's either going to be a period, which you guys know period. We've talked about that already, right? A period is a length of time. Or the other possibility is it could measure what's called a wavelength. Okay. A wavelength would be a distance. A wavelength basically refers to like how far has it traveled. Now I'm not talking how far up and down it's traveled. That's a little bit different here. But this would be like how much distance has it actually put between it from here to here, and how much horizontal distance from here to here has occurred. I've got some more pictures to show. So here's a possibility. We could talk about an amplitude in terms of how tall the graph is. But along the other axis, we could either measure the units and say like from here to here, this took 2 seconds. You could say that. If it took 2 seconds to go from here to here, how far would it take to get from here to here? Well, also 2 seconds, right? How far would it take for you to get from here to there? Yeah, 1 second, right? Wouldn't it be half? Isn't it kind of symmetrical looking? If I asked you how far it was from here to here, well, that'd probably be half a second, right? Half a second from here to here, half a second from here to here, half a second from here to here, half a second from here to here. So you could measure the y-axis basically in time. We wouldn't call it time, but we would call it period. Basically, how long is it going to take for the second repeat? The other thing we could do, though, is we can measure in terms of distance. Right? And so you could say, well, how much distance has actually occurred from here to here? Right? For example, imagine this is a wheel traveling around in a circle. Okay? And so essentially, imagine you put a chalk mark on the top of the wheel. Here's the top of the wheel up here, and as the wheel rotates, it comes down, and then it comes back up, and then down, and up. Right? If that makes sense. I might ask you, after your wheel has rotated 1, 2, 3 times, I might ask you, how far has the car moved? That makes sense. How much distance has the car undergone? That, by the way, is different than the amplitude. The amplitude in that example would be how big is your car tire. Right? The bigger the wheel, does that make sense? That would be your amplitude. From here to here would be the distance traveled. But again, we don't actually use the word distance. We have a different word for it. We call it a wavelength, and this is the symbol we use for wavelength. It's like an upside down Y. I've forgotten off the top of my head what Greek letter it is, but it's a Greek letter. I think it's lambda, maybe. I'm sure it's in my notes later if it's relevant. Anyways, long story short, when we talk about these graphs, along the axis, for the x-axis, it's going to be either a meters value, which is known as a wavelength, or a seconds value, based on period. Here's some more definitions. And these ones are not so much math-based as they are physics-based. But there's a lot of similar concepts. For you guys in my grade 11 class, we just are working on quadratics, right? Well, quadratics are defined very much by the fact that they either have a maximum value or a minimum value, right? Like a vertex. Well, we don't call these things here a vertex. In a way, though, doesn't it kind of look like if I just cut off the graph right here and cut off the graph right here? Doesn't that look kind of like a quadratic graph in a way? And they have very similar properties. Except rather than being just one quadratic graph, it's like, well, here's a quadratic that blurs into another quadratic, blurs back again. And so it just repeats over and over again. In math, we might call this a vertex. Sometimes I call it a turning point.
Gerald Henderson, can you please come to the office?
But
Gerald Henderson, please come to the office.
In terms of physics, you guys can see the labels there. We call them crusts, or either troughs or troughs, however you want to pronounce that. I don't really care. But basically the highest or the lowest part, right? A peak of a mountain or the lowest part of a valley. Sorry, what was that? Oh, okay. Let's say that you found the distance between two crusts. If I asked you for that distance, what would we call that then? A wavelength. If I asked you for the period between two of them, no, I could give it away there. If I asked you how long it was between them, then that's a period. Does that make sense? Okay. From one to the other is basically half of that, right? Like that's the halfway point. From here to here is half of from here to here. Makes sense? Okay, I have some other words on here that are not labeled. So I'm going to add to this diagram if it's not too messy. They're called nodes and antinodes. A node would be found right here. Those are known as nodes. Basically, they're defined by when something is in what's called the equilibrium position. In math, what would we call these points right here? Yeah, x-intercepts are the math term for, in physics, what we call nodes. How far is it from one node to the next node? Maybe I'm not phrasing that very well. If I told you that from here to here was 2, whatever, 2 meters, 2 seconds, 2 anythings, how far would it be between the nodes? Half. Can you guys visualize that? If from here to here, the distance between crests was 2 units, from here to here is half of that. Maybe here's how I can explain that. If from here to here is 2, then from here to there should also be 2. You can kind of visualize that. Basically, pick this up and slide it over X amount. Pick this up, slide it over also X amount. Right? Well, then from here to there should be half of that. You're going to get a lot of theory questions in this section here. And hopefully you'll find them to be more or less straightforward. I'll say, well, from here to here is 5. And then I'll put some other location on there and say, well, how far is it from here to here? And you'll just have to use kind of your spatial awareness skills, try to figure out how far either like from here to here, we define that as a period or a wavelength. From here to here, then would be half of that. By the way, the other term you need to know is called an antinode. Antinodes are like the maximum displacement. So the crests and the troughs, they are the antinodes. So think of a pendulum swinging back and forth. When it's in the middle, it's a node. And when it's at the maximum amplitude, it's an antinode. Here's a word I've been using. I just haven't got to the slide on it. Amplitude then is a measure of how big the wave is. So some waves are taller than each other. Basically, if you can figure out how tall the wave is, that's amplitude. What does amplitude do to, say, a surfing wave? Well, it just makes it a bigger wave, right? But what would amplitude do to a sound wave? Makes it louder. Good job, yeah. Amplitude makes a wave louder if it's a sound wave, for example, right? It makes it a more powerful sort of wave to be able to pick up, if that makes sense. The frequency affects the pitch, if that makes sense, right? So when I was hitting the glasses one day over there and using the tuning forks, basically, the frequency is how often it is from, like, say, here to here. You guys remember, like, well, that was a period? You can convert period into frequency. That distance refers to the pitch of the sound. You guys know how you have like well, maybe you still have a radio in your car? You can tune the radio to like 101.3 FM or 920 AM. Right? Basically, that is also a frequency of the wave. Right? And that will basically tell you, is the wave a very long wave like this, or is it doing this? Okay. If you have a very long wave, that is a low frequency. It's not occurring very frequently. If you have a short frequency and it's buzzing up and down like this, then this might be the radio station of 107 point, no, this would be like, say, 107.7, and this might be 91.2 on your FM dial. This is a very small frequency because it's not happening very often. This is a very, very high frequency because it's happening very quickly. You see how I've tried to draw them with a relatively similar, I didn't do it very well, but this distance from here to here, if I drew that similarly, that would be the amplitude. And that would be your strength of signal. If you had a very strong signal, it would be going very, very high up and down, which means your car could pick up that radio signal very easily. Right? A very weak signal would have a small amplitude. You guys see the difference there? So, amplitude basically is how big the wave is. Maybe here's a better way of putting it. How much energy it has. If you're talking a sound wave, it's kind of weird to think of sound as energy because we don't normally account for it in all of our other energy use, but I mean, sound is a form of energy, right? So the bigger the amplitude, the more energy it has. If I speak in a quiet voice, I'm not giving very much energy. When I really yell, right, then I'm providing more energy. Same thing with your wave when you're riding as a surfer. Same thing with an electromagnetic wave in the stereo of your car. Here's the terms I've been using already, just another definition of them. Period and wavelength then is basically how far is it from here to here? How far is it from here to here? That makes sense? So the more frequently it happens, that changes the pitch of something. If it's an auditory signal, then if the wavelengths are squished in, if you were to have something that looked like this, that makes sense? See how it still has the same amplitude, but it's happening more frequently? This would have a higher frequency, and then by having a higher frequency, it has a higher pitch. Right? If your ears could pick it up, you'd hear higher, right? Your ears can't actually hear the pitch that's emitted through your stereo, right? But the stereo is able to recognize that signal. Okay, I'll move on. Oh, I did have it written here. This is called lambda. I was right. So just so you know, in terms of what we call that symbol, the upside down Y is lambda. Okay, another couple sets of definitions. When I drew a picture of a wave, I'm really trying to draw it as though it's only going in one direction. Right? You can imagine that as I speak, sorry, that's not sense to you guys, but I'm emitting waves. And this wave is going up and down and up and down and up and down and up and down until it reaches you. But when you look at that up and down motion, that's only in one dimension. My waves actually go that way and that way and that way and that way. Does that make sense? So sometimes what we'll do is we'll draw a diagram like this called a wave front diagram, where you have to kind of imagine that's what's happening here, is that this is me speaking, and here my words are going to Baron, here they're going to Rebecca, here they're going to Darian, right? They go in all different directions. But I really can't draw this like up and down in that same way, because this is more like a top-down view, if that makes sense. So what ends up happening is all of these lines are intended to be the crests. Right? So if you can imagine that this was like a top-down view, if you could like flip it and look at it from like a side view, this right here is like the top of a wave. The middle would be the bottom, that would be the new top of a wave. The bottom, the top of a wave, the bottom, the top of the wave, as it gets sent out in all directions. And so we just kind of draw it like this to help recognize the fact that this is really three-dimensional. Right? It's not in one or even two dimensions. Can you guys visualize how that's supposed to work? So these lines represent the top of all of the waves. Like that. Here's some other diagrams to kind of maybe help illustrate the point. Imagine that you had a body of water and you dropped a rock in it, or this picture I found here, they just like kind of dabbed, I don't know, something in there, right? Can you guys kind of see how, there is a wave right here where there's like a top to the wave, there's a bottom, there's a top right here, there's a bottom, there's a top, there's a bottom, there's a top. Okay? And so what we were drawing here was really the completely top-down view, whereas this one's kind of taken at an angle, so maybe you can kind of see that concept, right? And again, when I talk about, like, say, when you send out signals, whether it's your cell phone, whether it's the radio, microwaves will even emit signals like this. I don't know if you guys have ever noticed this before, but in our house we have baby monitors because my daughters are little, right? And baby monitors work on a certain frequency. When we turn the microwave on, the microwave actually emits the same frequency of radiation. Now, granted, it's inside the microwave trying to heat up your food, but it actually emits the same frequency as our baby monitors do. And so as soon as we try to heat something up in the microwave, our baby monitors stop working. Right? We actually have a word for that. You know what the word is? Interference. When something gets jammed, basically, it's because you're trying to find a way to jam different signals. So, anyways, long story short, there are so many different types of waves. Most of them we don't even see, right? The waves to your cell phones, right? Your cell phone really has a couple of different waves that need to get sent to it. One, it's hooked up to Wi-Fi, so that's one frequency it's emitted to, right? But two, you probably have a 3G signal hooking it up to the satellite so that you can actually make a phone call. Does that make sense? So there are multiple different waves being sent and received from your phone. Right, anyways, I'll move on. Here's what I need you guys to be able to do. I need you to be able to write a rough mathematical equation for a wave. And it's very simple. You only need to know two things. You need to know the amplitude, and you need to know either the period or wavelength. And these are kind of generically how the formulas go. Grade 11, you know how you're kind of working on this in our class right now, where I give you information and you have to write yourself an equation? This is kind of the grade 12 version of it, only on a pretty basic level. This A value right here is a leading coefficient. If you have that leading coefficient, awesome, just plug it right into the equation. This value right here is either your period or your wavelength, depending on which one you have. Anyone have an idea where the 360 came from? Yeah, just 360 degrees in a circle. Okay. If we were working in radians, we would use 2 pi, because that's actually the equivalency in radians. But for the purpose of this course, we're just going to keep it simple and just always make that 360. So this is kind of our generic formula for writing an equation. Let's give an example here. Let's try to sketch a graph for a wave which would have an amplitude of 2.5 meters and a wavelength of 10.5 meters. No, I did that wrong. Y equals a sine of 360 over, I'll just leave it blank for right now. Okay, well, if I tell you your amplitude is 2.5, where's that number go? Yeah, it's your leading coefficient. So y equals 2.5 sine. And if I tell you the wavelength, it just means you take 360 right here and you divide it by 10.5. There, we now have an equation. Let's graph it, see what it looks like. So y equals 2.5 sine of 360 divided by 10.5. I'm going to do zoom 6 to start here. That's not bad. If you have what I have there. I've got a, wait till it goes up and down. Oh, I should be in degrees though. Oh, okay, that's a little better. You guys able to get something like this in your calculators? I'm just negative 10 to 10, like just a standard one. Let me know if you can't get this. Is it working, Michael? Or no, it's not working. Check and see if you're back in radians rather than degrees. Because I might have flipped it into radians, or you might have flipped it into radians when I was showing you that earlier.
Once I change so it goes out.
Sounds good. Okay. Okay, let's talk about how to confirm that our amplitude and our wavelength is actually what it says it is. You guys remember how to, in your calculator, find like a maximum or minimum? What I would recommend here is, let's find the minimum value, say right about here. So I found the minimum is at x is at negative 2.625002. And y is at negative 2.5. That helped me confirm my amplitude. Because the amplitude is supposed to be 2.5, right? Well, by virtue of this value being negative 2.5, it means that we've gone down 2.5. If we've gone down 2.5, we must have gone up 2.5. So that's good. I'm going to then find the other minimum value just to confirm. So I'm going to find consecutive antinodes. That's the word we're going to use, is antinodes and nodes. So if I find the other value over here, it's going to take a while to get there. Okay, if I find the other point here, it's at 7.875008, and again, negative 2.5. Well, the negative 2.5 I expected because that's the amplitude. It should have gone up or down 2.5. But it's the x values that I really care about. What's going to be special about these consecutive x values? And how far apart should that distance be? Hopefully 10.5. Right? If you were to take 7.875 blah 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 and subtract negative 2 point whatever that number was there, hopefully you discover that they differ by a distance of 10.5. Does that make sense? So it's pretty straightforward. I'm probably going to give you an amplitude and a wavelength. If I give you an amplitude and a wavelength, ooh, what happened there? This happened before once too, didn't it? Green screen of death.